Hey everyone, welcome to this explainer. Today we're doing something pretty cool. We're going to completely decode the microscopic rules of matter to understand exactly how we separate and purify the incredibly complex world around us. Think about it. Literally everything you touch, drink, and breathe is a mixture. But how do we actually pull those mixtures apart to get exactly what we want? Well, we're going to find out.
It really all boils down to one massive question, right? How do we separate the invisible? How can we possibly untangle and identify specific substances when the particles themselves are far, far too small to see with the naked eye? It sounds like magic, but it's actually just a matter of hacking the physical rules of our universe. So here's our game plan for today. 1. Kinetic particle theory. 2. Phase changes explained. 3. Paper chromatography. 4. Distillation methods. And 5. Using a separating funnel. Let's jump right in.
All right, Section 1, Kinetic Particle Theory. We've got to establish the ground rules of the physical world first. Because before we can break mixtures apart, we really need to know exactly how they behave.
Okay, so looking at the overarching law of the land here, all matter is basically dictated by just two things: exactly how its particles are arranged and how much kinetic energy those individual particles actually have. Literally everything else flows from those two fundamental facts.
We kind of know the drill here, right? Solids are locked tight in these regular lattices. Liquids? They're more like a sliding crowd. And gases? Well, they're your rapid, random rebels with tons of high kinetic energy. Now, these distinct structural behaviors, which are driven entirely by intermolecular forces and particle movement, these are the exact levers we're going to pull to separate them later on.
Moving on to Section 2, Phase Changes Explained. Let's see how all this builds up when we actually transition between these states through melting or boiling.
Now, here's a fact that absolutely trips people up, and honestly, it feels completely counterintuitive. Think about it. If you put a pot of water on the stove and crank up the heat, you'd totally expect the temperature to continuously rise, right? But during the actual phase change itself, like the exact moment of melting or boiling, the temperature actually stays completely constant. Crazy, right? But it's true. So why exactly does this happen? Well, all that thermal energy you're pouring into the system is being used entirely to break the attractive forces between the particles. It's literally ripping the lattice apart, or, overcoming those intermolecular bonds. Because that energy is so incredibly busy doing structural work, it actually does not increase the kinetic energy of the particles. And since temperature is essentially just a measurement of kinetic energy, the temperature just doesn't budge until the phase change is 100% complete. All right, on to Section 3, Paper chromatography. Now that we know the rules, let's look at our very first scientific hack. This is an awesome technique that essentially weaponizes different solubilities to separate out mixtures. Let's walk through the setup. It's pretty straightforward. You take your stationary phase paper, and first things first, you draw a baseline. But notice, this baseline absolutely must be drawn strictly in pencil. Why? Well, because graphite is completely insoluble in chromatography solvents, it just won't run. If you were to use a pen, the ink itself would dissolve and separate into its own dye components, totally ruining and contaminating your results. So once you have that safe pencil line, you apply a spot of your mixture and just let the mobile phase solvent creep its way up the paper. Now, as that solvent travels up the paper, carrying the different substances at different speeds based on their solubility, it creates this visible line. We call this the solvent front. It represents the absolute furthest distance reached by the moving solvent. And honestly, noting exactly where it stops is a vitally important measurement for the next step of our analysis. And here's why it's so crucial. By comparing how far a specific substance traveled against how far that solvent front traveled, we get the RF value. It's a really simple calculation, just the distance of the spot divided by the distance of the solvent front. This gives us a characteristic ratio. Think of it like a chemical fingerprint. No matter how big your piece of paper is, that specific ratio will always be exactly the same for a specific substance in a specific solvent. This is exactly what allows us to perfectly identify what was hiding in our mixture. But wait a second. What if your mixture separates into completely invisible, colorless spots? Amino acids, for example, don't actually have a color. So how do you see them? Well, you have to use a specialized locating agent. You basically just spray a chemical like ninhydrin right onto the dry chromatogram. It then chemically reacts with those invisible spots to produce highly visible, brightly colored spots. And just like that, you can finally measure your RF values.
Okay, section 4, distillation methods. Let's pivot to our next set of tools and look at how we can go about hacking boiling points to separate liquid mixtures. Looking at our next tools here, we can see two primary purification methods detailed. And both of these rely heavily on those phase changes we talked about earlier, specifically vaporization and condensation. Now, the trick here is that we have to choose our distillation method based entirely on the specific mixture sitting right in front of us. Simple distillation, that's your go-to when separating a volatile liquid solvent from a non-volatile solid solute. Basically, you use it when there's a massively large difference in their boiling points. Salt water is a perfect example for this one. But fractional distillation, that is the absolute heavyweight champion for separating completely miscible liquids, liquids that fully dissolve into each other, that happen to have very, very close boiling points. Let's break down the mechanics of simple distillation first. It's brilliant. You heat the solution until your solvent reaches its boiling point and vaporizes. That vapor then escapes into a specially designed condenser jacket. This jacket is cooled by a continuous flow of cold water, which basically forces the vapor to condense right back into a liquid, dripping out the other side as completely pure distillate. But if we're dealing with those really closely matched boiling points, we have to add a super vital piece of hardware, the fractionating column. This column is just fantastic because it's tightly packed with little glass beads. These beads provide a massive surface area, which creates this perfect environment for repeated, continuous condensation and vaporization cycles. The vapors literally fight their way up, condensing, falling back down, and vaporizing over and over again. This ensures that only the component with the absolute lowest boiling point manages to make it completely to the top and distill over first. It's an incredibly precise sorting mechanism. All right, last but not least, section 5, using a separating funnel. We've talked a lot about miscible liquids, but how do we tackle liquids that simply refuse to mix together at all? Enter this separating funnel. This elegantly simple piece of glassware is used exclusively to isolate two immiscible liquids. The classic example here is oil and water. Because they just absolutely won't mix, they naturally separate into distinct layers based strictly on their different densities. And the operation honestly couldn't be simpler. You just place the mixture in the funnel, allow the heavier and lighter liquids to stratify, and then open the bottom tap. You let the heavy layer drain out and use the valve to perfectly cut off the flow the exact moment the lighter liquid drops. Gravity basically does all the hard sorting work for you. The heavy liquid is separated, and the lighter liquid remains safely trapped inside the funnel. So when we step back and look at all of this, a really clear picture emerges. By understanding the invisible rules of matter, we can untangle the physical world, whether it's the vibrating lattices of a solid, the energy required to overcome intermolecular forces, or differing densities and solubilities. Exploiting these specific, predictable behaviors is exactly what allows us to pull apart and purify almost anything we encounter. So think about the wildly complex mixtures you interact with every single day. The food you eat, the products you use, the air you breathe. Knowing that they all obey these exact same microscopic rules, and that every single substance has its own unique chemical fingerprint of solubility, boiling point, and density, what invisible mixtures could you untangle next? Thanks so much for joining me on this explainer, and keep looking for those invisible rules in the world around you.